expecting it to be recorded.
Great. So I'd like to introduce Thomas Braun, who is the founder of a physics software development company called Byte Physics, and has done a lot of work, especially with the Allen Institute, in designing acquisition software for their large-scale intracellular electrophysiology experiments. And on top of all of that, he has been a major contributor to the open source NWB ecosystem core components, in particular the validation and also several aspects of the API, ensuring that the standard, he's really been integral, particularly in the intracellular electrophysiology part of the standard, really shaping a lot of the infrastructure that we currently have there. So here he'll be talking about integration with MIES, a system for acquiring intracellular electrophysiology, I believe. So we're really to have you, Thomas, as part of the team and to have you talking here. So really appreciate it. And with that, I'll let you take it away.
Okay, thank you. Thank you for the introduction, Ben. I'll just also mention that I'm not alone presenting. I'm also one of my co-presenters is Tim Jarsky, who is my project manager at the Allen Institute and the original one of the original developers of the MIES software package. And yeah, and I would say I'll just share my screen and then we can start. So you should see a screen with a slide I did for another NWB IC Fish-rated talk last year. Just to mention it, we are a small crowd, so please feel free to always ask questions, either written in the Zoom chat or just turning up your mic and start asking. Yeah, what is intracellular electrophysiology? This is the idea is that you have slices of brain cells and you look at the electric properties of these slices, and what you do, you have electrodes, you contact or puncture the cells, you send in electronic signals and you get responses back. You also get, you can then either look at the response from the same electrode, or you look to the response of a cell which you contacted with another electrode which is nearby. And yeah, and that's it. And that's a technique which is pretty, yeah, it's pretty standard. It's nothing too fancy in principle, but of course, if you start diving into the into using it on a large scale facility like the Allen Institute, or if you want to really like do a lot of fancy stuff, the stock software doesn't work that well. So therefore, one of the things which were developed as for helping doing large-scale acquisitions is the MIES software package. And well, and a couple of words, I mean, what MIES already helped in doing. So there are two of the projects which use MIES at the Allen Institute. That's the single cell characterization work, which is abbreviated to IVSCC, and the synaptic physiology project. And the MIES software package has tremendously helped in achieving the goals of these projects. For the IVSCC, it was possible to obtain around 10,000 quality control and standardized recordings from neurons, so 10,000 neurons and a lot of more recordings. And for the synaptic physiology project, more than 20,000 pairs of synaptic connectivity were acquired, and that's a big number if you're into intracellular EFIS. And there are also a couple of outside research lab using MIES, but at the moment, most of the development and comes from the Allen Institute, or as myself from consulting for the Allen Institute. And okay, a few words in case you've not heard about Igor Pro. It's a really cool program. It's an integrated development environment for doing scientific work on data, for doing engineering work on data. Yeah, you can create, you can load in data, you can apply math, do plotting, do all the things you expect from such an environment. It's a bit like MATLAB, but yeah, I mean, just in case you know MATLAB. And okay, so let's dive in to what is MIES. We have, so first of all, let's start with a quick demo. And what we do now, we just load up our standard configuration, which we saved earlier. And so this would be after you've prepared your slice. So from the experimental setup, everything is working. You just click here, or you can even use a shortcut, but I didn't use a shortcut for explanatory reasons. And now everything is starting to be set up. Inside MIES, we have JSON style configuration files where you can write what your setup should be. And this works in a way that you say, okay, control XYZ should have a value of 10 in the config file, and on opening the config files, these settings are then applied. And this is now, so I've here an ITC18 USB digital analog converter, which is from Instrotech Hacker. We also support, in case you don't have one of these old DACs, we also support NI hardware. We have a list of supported hardware on our website, and that is Allen Institute/MIES. We have a list of supported hardware where, and you can just go there and have a look. So basically, it's like 2 NI devices and the ITC18, ITC16, and the ITC1600. And you can also use multiple DACs in parallel. This is also no problem. We are really have a focus on scale so that we can really use max out the efficiency of the experimental setups. And so what we are seeing here now is, so this is the main data acquisition panel. And it's currently, I've activated 2 head stages. So in NWB lingo, it's always called electrode, but an electrode is the exact same thing when a head stage. In MIES, it's just called head stage. And yeah, so I have 2 head stages active. One is in voltage clamp mode, the other is in current clamp mode. We are interfacing with an amplifier. We are interfacing with the default amplifier, which a lot of people are using. It's from Molecular Devices, the 700B. I'm actually using a demo version here because I cannot really justify spending 30K on an amplifier just for software tests. But yeah, for this now, the demo version works as well. And yeah, and what we're currently doing, we're currently running the test pulse on each head stage. And yeah, and there's a lot of things you can tune in. There's a lot of things you can tune in the software. For example, I mean, if you would, let's say, okay, you want to change the clamp mode on the electrode, well, you just click, and you can also do it like that, and the software will just do what you expect when you change clamp mode. What you can also do, you can just you can stop the test pulse, you can start it again, and you can tweak the duration. You can do things like having a longer baseline, having a shorter baseline, all that. You can tune the amplitude for voltage clamp and current clamp. You can basically set anything you want to set for doing your intracellular work. And so, as I mentioned earlier, we have auto-configured the setup here. So we have already selected two stimulus sets for these two channels. So after loading the automatic configuration, we can just hit acquire data, and it's acquiring data. And it's also doing that now for 25 sweeps in total, because I've told them to repeat sets, and one of the stem sets has multiple sweeps, so it will just keep acquiring data. And as this is a NWB hackathon, I also would like to mention that we're already exporting our data into NWB version 2. As we were a very early adopter of NWB, we still support reading and writing NWB version 1 data, but we encourage everyone to switch to NWB version 2 because our version 2 support is much more sophisticated. We follow all good practices, so we embed the specification. We have a MIES extension where we cache the specification for. We have, as part of our automated testing, of our CI testing, we we create new NWB files and validate them against the latest PyNWB version. And therefore, yeah, a lot of work has gone into the NWB support, especially into the NWB version 2 support. So let's use version 2 and only use version 1 for reading the data. And one of the things we're currently moving to is so we have a lot of documentation on our GitHub page, but that's mostly for developers, and we're at the moment fleshing out the important parts and adding screenshots and screencasts for the documentation parts, which are actually targeted for users. So yeah, this is an ongoing project, as you can imagine, and therefore, yeah. But I mean, you can just subscribe on GitHub and get notified on the relevant changes. If you're trying it out, you're at your home, you might be first of all, you don't have to fiddle with any installation or so. We have an Windows executable as an installer, and you can just download that from the GitHub page. And if you have Igor installed, it will do the right thing, and you just start up and you have the MIES panels here, and then you're good to go. And also, although we are still lacking a bit in user documentation, what I would like to point out is that every control has a short help text. I hope this works in Zoom now. So there is a small pop-up on every control, what it does. And therefore, you can get quite a good sense without having to consult our yet to be written manual. Yeah, as I said, there's a lot of explanations. And yeah, but of course, MIES is not only acquiring data, so and we can also, so I only have shown you here two electrodes with each an DA and AD channel, but of course we also have support for TTL data. So if you want to trigger something like, I don't know, an LED or something like that during data acquisition, the easiest thing for timing purposes is usually to use a TTL wave, and we do support that. And of course, we also export the TTL data to NWB itself. So this is also something which we really take very seriously in MIES. So we do collect a lot of metadata when acquiring the data, and we export that all into NWB. One caveat is we use a NWB extension for that, but we hope to leverage the new NDX ICFIS extension at some point to store our data in a more generic way. And yes, so this is the main, as I said, this is the main data acquisition panel. But of course, you not only want to acquire data, you also want to look at it. And this is where our very creatively named data browser comes in. What you can do, well, you can browse your data. You can, now we're only displaying the AD data, but of course you can also just look at the DA data. You can do things like overlaying sweeps. For example, if you think, okay, yeah, this is now, we're displaying now sweep 21, but maybe what's the difference to sweep 20? And maybe the DAs are now a bit confusing. So let's just look there, and where we see, okay, so we seem to modulate something from the sine or from the sawtooth here on each sweep. We have the, so as I said, we have this kind of metadata storing approach where we store everything we can get our hands on, and we store that in what we call a lab notebook. And you can browse that pretty easily. For example, if you want to look, okay, well, let's see, what clamp mode did I use? And you can then get a plot with, yeah, the clamp mode of each sweep number. And here you have a legend which head stage is which color. The coloring of the data is the same throughout MIES. So if you see a yellow curve, it's from head stage 2. And if you see black, it's from the first head stage. We have not only entries like clamp mode, so what we call amplifier metadata, but we also have things like the stem set wave name, which you can also zoom in here, of course. Yeah, you can see, okay, this was sawtooth on the first head stage and sine on the second. And of course, we have documentation. We have, if you want to read that, you can just use our standard functions for reading the lab notebook. We have documentation how the lab notebook looks like. And we have also linked code for Python to read the lab notebook. So if you want to get a head start here, that's pretty easy. And as I said, the lab notebook is always stored in the NWB file as well. So you have all the data you need in one place. And yeah, so we have acquired data, we have looked at the data, but what we have not yet done is how to create the stimulus sets. Well, we have the stimulus sets are created in the wave builder. So this is the application where you can create stim sets. We support the usual epoch types, so a square pulse, a ramp, MIES, sine, sawtooth, pulse train. But we also support, for example, let's say you already have your stem set, which you created by some other method, and it's like now a numeric array, well, you can just load that in as well. You don't have to do anything. You can just import that into Eiger, select it here, and you can use that. Or if you're more like someone who wants to like use building blocks on top of each other, you can also use the combine tab epoch type, where you can combine two stem sets. So for example, we can here say, okay, well, my new stem set should be A plus B, and probably that will not work, but let's see what we, yeah. So this is now sawtooth plus a sine. And you can do all the math you want to do, and you can also use fancy functions and all that. But yeah, this is, and we even, so one of our main approaches is that we want to keep things reproducible. So if you now store that, so let's say, okay, yeah, we want to save that stem set. It's a combine set, and we save it. And if you now export that into NWB and you load that in a later version of MIES into MIES again, it will be recreated in exactly the same way with stem set, and you can use the exact same stem set. The same is true for noise stem sets, and we really take great care in allowing you to reuse what you know which works, and you don't have to fiddle with version upgrades or stuff like that. We always do that under the hood for you. And okay, so but let's create a very simple stem set. We want to have a stem set with, let's say, 3 sweeps and well, let's use 5 sweeps and 3 epochs. And the first epoch is a square pulse, which, well, let's say 500 milliseconds, amplitude 0. The second epoch is a pulse train, where we use 1000 duration, 1 amplitude, 10 frequency, and 25 milliseconds pulse duration. And the third epoch is a square pulse again, and this time it's probably something like 750. Okay, so this is now our 3 epoch stem set. We have square pulse, pulse train, and another square pulse, and you can now go on and combine all of them. We support 99 epochs in a stem set. This was enough until today. If it's not, yeah, please ping us and we'll do some thinking how we can increase that or help you achieving what you want to do. We also have a limit. Well, it's more like a technical thing that you don't mess up your stem set. So it's like stem sets are limited to, at the moment, to 30 minutes. We don't expect anyone to come even close to 30 minutes, but it's just a limit that you don't create huge stem sets, which might prolong some applications. So if that really is a limit for you, yeah, contact us and we'll raise that arbitrary limit to something larger. And okay, so we've now created that stem set with the 3 epochs. And what we also have is what we call the delta mechanism. And you can say, okay, as I said, we have 5 sweeps now, but with 5 sweeps, I mean, we're now the same. So you have 5 times the same stimulus set. But what you can do now, you can say, okay, well, I want to modify something on each iteration. So you say, okay, this is a delta value of 0.2. And then you have, so the first stem set has an amplitude of 1, the second has 1.2, 1.4, and so on. And as you might imagine, with all these controls here, we do support a lot of different delta methods. So you can not only use an increasing value, you can also use a power, a multiplier, and you can use all fancy math. And at some point we realized, okay, well, we never gonna get get all the methods we need implemented. So we also support an explicit list where you just supply the values you want to have as delta values, and you can use whatever you want as values. And of course, the delta values are supported for all parameters here, and we have a lot of fine tuning which you can do, or choosing different ways. And yeah, so, and with StimSet, we just need to save that. So let's save it as square PST square, save it, and we select it here and we run it. And let's use only one sweep now. And yep. And so this is a setting, activate the test pulse after data acquisition so that you're always in test pulse mode, because that's, as I've been told, I'm an engineer, that's much better for the health of the cells. So we also support that. And so as I said earlier, we have like this export to NWB setting here. So this is exported directly after data acquisition. It's exported to NWB. Right now, we don't support that you then start reading the data from it and do your analysis. This is mainly for performance reasons, because HDF5 itself does not support arbitrary reading and writing concurrently, and we don't want to close it every time we write into it, because that will be, for performance-wise, not so good. And okay, so the next thing I wanted to, yeah, so as I said, we are storing every sweep into the NWB file. But if, for example, you say, okay, well, actually, you don't need it on a sweep by sweep basis, the data, you just want to do it at one click at the end, or of course, you can always automate everything. We have a lot of public APIs, a lot of methods you can tune MIES. You can also call in from other programming languages into MIES. So if you want to remote control something from, I don't know, Python, C++, JavaScript, whatever, you can just do that. There's a lot of use for that, and a lot of advantages. For example, if you have already some framework which does some parts of your data acquisition, and MIES should only be part of that, you can just remote control MIES, get your data out, export into NWB, and then start from there. So here we have the option to export your data into NWB, so all of the acquired data, in case you didn't save on a sweep by sweep basis. So we're just doing that now, and it's using the folder which we told him to use in the config file. So you can also avoid getting confused with your files by using the config file. And if you now just save that, it takes around like a couple of seconds. Yep, we're done. And we've now created a NWB version 2 file, and it's schema compliant. So as I said, we check that during as part of our testing. And so this is an HDF5 browser integrated into Igor. And if we now browse that, you will see all the things in case you've ever looked into an NWB file, ICFS file, all the things you know. We have the acquisition group with the single time series here. We have links to the electrodes, the devices. We have, as I mentioned, we have the specifications cached here. So this is ready to be uploaded if you want to Dandy, or you can read it with PyNWB and do further processing, or you can use MetNWB. Or you can also use our IP NWB interface for reading and writing NWB files. And yeah, okay, specifications are here. We store the presentation time series. We store the raw stimulus sets. Stimulus, 1 second. Where do we have the stimulus? Stim sets here. I always think it's a group. Yeah, so we have these internal configuration files for the stem sets, and these configuration files can be read into MIES and then recreated, and that's it. So yeah, so this is the but of course, I mean, nobody wants to browse NWB files with a plain HDF5 browser because that's pretty inconvenient and not very nice to use. So in MIES, if you have stored NWB files, you want to use the analysis browser for browsing your acquired data. And this works like, so you select a directory here, and then the folder is scanned for you. So we now have multiple files found. So we have, so this is the NWB file we stored during data acquisition. This is the NWB file we just exported, and this is the PXP. So this is the Igor experiment where everything here lives in, but as we haven't saved that yet, there is no sweeps there. And what you can do now with the analysis browser, you can, well, if you want to just open that and load the sweeps from here, you will see, okay, so this is now on a sweep browser window, which looks exactly like the data browser, except that the lab notebook browser here is not present. And yeah, you can do all the analysis you want on that data now. You can overlay it. And the nice thing about the sweep browser is that it allows you to open data from different experiments. So let's assume these two experiments would be have very different data. You can say, okay, I want to load sweep 5 here, and I want to load sweep 7 here, and then I do load sweeps. And oops. Okay, and then that did not work. Okay, sorry for that, but yeah, so the idea is that you have here. So I'm using my private development version here. You can browse existing data. You can cross-reference that from different. You can open sweeps from different experiments. So this allows you to use your data in the most efficient way. And so now we have acquired data, we have exported it into NWB, we have reloaded it into MIES again. What you can also do in MIES is you can do online analysis. And this means that you can, for example, we call that the sweep formula. You can, let's turn overlay sweeps off. For example, let's say, okay, well, you want to do something with that data here now. You can, for example, here we have a integrated scripting language, which basically allows you to do math on your acquired data, but not only basic math, but also specialized functions for intracellular electrophysiology. And here, what I'm doing here, I'm just taking the data. I'm using a cursor range. So let's say, okay, you want to have cursor A, cursor B, and here you have now. So this is now the head stage 0, and this is then head stage 1. But if you say, okay, well, actually, I don't want to have both head stages. I only want to have one. You can just say, okay, well, let's just use AD1 data. And then you can just extract that part. And you can also say, well, I want to do things like, okay, I'll take the minimum from that. And this is this value. Or you can say, well, I want to have the minimum and plot that versus the mean value of something different. And we use now the cursor range again, but we use now from the AD0 channel. And if you do that, of course, the Y value didn't change, but the X value changed. And well, of course, I mean, this is now, well, it's steady, it's pretty, that's pretty nice, but still what we also have done is that we've integrated updating that into our workflow. So whenever you acquire new data, this is then so as you see, so this is okay. We turn on repeated acquisition, and now you see that on every sweep display, this formula is executed and the graph here is updated. So there's a lot of things you can do. You can also set these formula, of course, with the configuration files. So you can have standard analysis for specific experiments. And what you can also do, you can not only do these kind of like basic math things, but you can also do things like find levels, find the number of level crossings. You can count the number of action potentials in a data set. So we have a lot of, and for that, of course, we have documentation. So we have it either directly here accessible for everyone, or we have it also on our GitHub page with the HTML created by Sphinx. You can access the lab notebook from the sweep formula here. So this means you can plot against lab notebook entries which were acquired as metadata, or if you want to get really fancy, so things like what IVSCC does, they write lab notebook entries from from analysis they do during data acquisition. So we have something what we call analysis functions, and that allows you to call code during data acquisition at certain points. And this allows you to do really fancy stuff. I mean, you can do QC on your pre-pulse baseline, for example. And if you say, well, this doesn't look good, or it's too noisy, it has wrong value, well, you can either adjust some setting, or you can run the test pulse some more and reacquire with abort the current sweep and then start over. And this, of course, greatly speeds up data acquisition, because you don't want to run a 10-second sim set if you know after half a second that this will not be passing quality control in the end anyway. So you can abort early. And if no one has any question, I would quickly show you these analysis functions, because that's something which has really proven to be very helpful in day-to-day use, and also is something which really distinguishes MIES from other programs. So you have here your stim set, and you can then say, well, let's attach analysis function. I'll just use the test analysis function because that's easier to explain than the other specialized functions. And you select that here, and you say, okay, well, let's save it. And so the analysis function is part of the stim set. So you can, the stim set know which analysis function to run. And as long as the code is available in MIES, it will be run. And if we, for example, now run data acquisition again, so we have now added an analysis function to the square PST square stem set we created earlier on in the wave builder. And that is now, that's still selected here. And of course, MIES already got notified that this is now out of date, the stem set, and this will be recreated, and we'll have the analysis function. And for that, I think so this is the Igor command window where you can type in code here as well. But of course, we don't need to do so. But for the test analysis function, that outputs when it's being called, I think. Okay. That is not called. Let me check why this is not called. Yeah. Test analysis function weave free. Okay. Well, that's interesting. Why do we? Yeah, because it's not called because we told MIES not to call it. We have something. We have a setting here which is aptly named skip analysis function calls, because it might not always be that you want to call the analysis function attached to your stem set. So we have the option of skipping that. It's mostly something you will see on developer machines checked. So if we uncheck that and redo data acquisition, you see, well, that is called a lot of times. And you will see, so the analysis function just does a printout here. It fetches some parameters. You can also feed in analysis function parameters, which you define as part of your stem set. So you can, so basically the stem set can then set up the input parameters for the analysis functions for your QC or for your post sweep analysis. So you can also think about like, well, yeah, you want to set specific sweep formulas after running the stem set and visualize that and save that. So you can do that, all that stuff in MIES. And you might also have seen, so there's a lot of different events where we call the analysis function, and you can then respond either to that event, do something, or just ignore it. And the event which is called most often is the mid-sweep event, and that is really called during data acquisition. So while the data is acquired, your analysis function is being called, and you can do stuff. And of course, you should not take hours to compute, because otherwise the measurement is then finished, because, I mean, we're not stopping it. We're just like sending you the current chunk of data we've acquired, and you can do something, but data acquisition is, of course, still ongoing, because if we would stop it, the data set would be messed up and you couldn't do anything with it. So this is just as a side note. And yeah, so, and for example, I mean, as we said, there's a lot of metadata stored in MIES, and what is also, of course, stored are things like, well, what analysis function did we use? And of course, analysis function starts with A, but we store it under generic function. So, and you know, if you now zoom in, you see, okay, yeah, so sweep 51 used the test analysis function we3, and for the other sweeps in the beginning, we did not have anything, so we don't have an entry here. And yeah, so if you supply analysis function parameters, these are also saved in the lab notebook. So there's, in the whole, we save more than 200 metadata entries, and we're currently in the process of documenting exactly what these parameters are. And so to give you a hand when you want to read that, and this will be finished. We target for this year. It's quite a large project to get that done properly, and we have already started that like months ago. And yeah, I think I'm done for showing you a very quick deep dive into MIES, what it can do, how it can help your measurements in for intracellular EFIS. And yeah, as I said, go to the GitHub site I mentioned. We have ready-to-use installers for Windows. It only runs on Windows because of hardware limitations. So the vendor libraries for the DAC and other parts are only available on Windows, so we don't run on Mac. iGoPro runs on Mac as well. And yeah, and if you want to use it, feel free to use it. You can tell us that you use it. You don't have to. Of course, we are always nice to hear about users using MIES. You're of course also welcome to join the development team if you're already using it, or if you say, well, yeah, this is really cool, but with 0.5% usage use cases, which is currently not handled, you want to get that done yourself. Yeah, feel free. I mean, it's always good in these cases to reach out first so that we can give you a hint how to start, or maybe what you want to do is already implemented and maybe it's just named a bit differently or placed in a different place than you would expect. So we're always glad to give you any hints you need. There's a lot of things I've not covered. Things like you can do asynchronous acquisition, meaning you can read out a temperature from some sensor which you just read in by a one-point data acquisition from an AD channel. You can, as I said, you can use multiple data acquisition panels at once. So if you have multiple ITC18s, or if you have multiple NI devices, an NI device or an ITC device, you can use them together. For some ITC models, we also still have support for like using them synchronously. For NI hardware, this is solved on a hardware level, so MIES only sees one device. But for older ITC setups, we also support that. What we also support is, and I haven't mentioned that here, is pressure control. So there are a couple of manufacturers which you can use so it's a proportion air pressure control device which you can use with a DAC device, and then you can start things like breaking into the cell and all that. And this is, I mean, yeah, we do support that, and it's actively used every day at the Allen Institute, and this is all that set up here. And yeah, I think I'm through. Any questions?
Hey, Thomas, really cool. I have a question.
Yeah.
Do you have a sense for who's using this currently? I mean, I know the Allen Institute is a major user. Are there other groups using this, or are you, or
Yeah.
is this kind of tailored to their use case?
Well, so the main development is of course sponsored by the Allen Institute. At the moment, we have one group in the Netherlands, the Mansfelder Lab. They're using that. So they're collaborating with the Allen Institute on a project. And so they were also using a Patchmaster before. And the guy doing the measurements, he like played around for like half an hour and he said, yeah, it's like really cool and he really liked it. And it worked out of the box. And there's a couple of well, so our documentation was down like for like half a day, like a week ago, and we got like 2 emails from different people who are saying like, yeah, your documentation doesn't work anymore. So,
the curse of
we're definitely,
success.
yeah, exactly. So we're definitely used in other places as well, but we at the moment we don't have a complete list of our outside users. And
yeah, it's always hard to monitor that.
Yeah.
Very cool. Thanks.
Yeah. Okay, there's one question in the chat from Liviu. And okay, so the question is, I'm wondering how can one modify an acquired experiment if the data are directly streamed to NWB? So our approach, so our idea, okay, so second part of the question, I guess quite often an experiment is never preserved as it has been recorded because many errors can happen during an experiment. So do you load the NWB and then modify it if you're not happy with the file? So we have the approach that we always store the raw data. So we store all the data we have acquired in NWB and then do the QC and then create new NWB files from that. And so therefore the streaming to NWB works because we're only caring about preserving what we already have. And we don't need to remove files later on from that set. I've seen PulseQ, not expert. Okay, second question from Liviu. I've seen PulseQ. Can you briefly explain in which respects MIES is better than PulseQ? I'm sorry, I don't know PulseQ. Tim, do you know PulseQ?
Good morning. So I've never used PulseQ, but I think I can address maybe 3 questions at once here, one by Ben, and then about this memory, or modifying the question you just addressed about modifying acquired data, and then also this question about comparing it to other pieces of software. So I think one of the things that distinguishes MIES from most out-of-the-box solutions that that are proprietary is that the experiments you can do are limited by the imagination of the developers, and often those developers are not scientists or not even directly work closely with scientists. So that's one difference about MIES, is like Thomas is the developer and I'm the experimentalist who has a viewpoint that I need to manage many different types of experiments that we carry out at the Allen Institute, and also to some extent outside of the Allen Institute now for outside users of MIES. And because of that, we're always trying to build a software tool that's generalizable, but also customizable. So I think that's one of the major factors that distinguishes us from other software programs. And I also want to touch on this idea of I'm not sure if I understand the question correctly about, modifying previous experiments. So for example, in PCLAMP, there's a long history of acquiring data and not actually recording it, saving it, and that that feature of pclamp really stemmed from times where memory was limiting. Nowadays, memory is not an issue. So we really strive to always keep everything. You can, choose what you keep later, but MIES will always keep all the metadata and the acquired data, except under very special circumstances, which we won't go into right now, such that you can always recreate what happened. And we think that's another important feature of MIES, because we have so many users. If an issue arises and somehow the user went back and deleted data, we really go to we really try hard to always keep those things, even though the user may not want to see them. We allow that in some cases, but we always make sure the data is there that we could reconstruct what would happen. And this helps just for troubleshooting, but it also really helps for recreating what happened in the experiment. So I'll just finish off on one final point. What distinguishes MIES from other software really it's that metadata. That is one of the big features. You can relate, you have the metadata for on every sweep, on every test pulse. It's always there, so you can always know what the conditions were of the experiment, such that you can create very standardized experiments, which of course at the Allen Institute is incredibly important. So I'll finish there. I've already spoken too much.
Thanks, Tim. Okay, I think we're done. It's for 4 p.m. sharp.
Yeah. Yeah, that was great. Thank you so much, Thomas. This is a lot of info, and we have it recorded.